with the second part, and that's about data layouts. So here again is the agenda, and we looked at the storage hierarchy so far, but now we look at how to speed up a system by improving its data throughput, and that has a lot to do with data layouts, and I'm not sure how many heard about that: row layout, column layout, hybrid, compression. I mean, you will have seen compression to one part or the other. I mean, JPEG or MPEG or zip files are used to save space on your storage device. We also use compression, but not to save space, but to increase bandwidth, and we will look at that in this chapter. Okay, so what we're looking at now is from a high-level perspective is how to map relations from our database system to the devices. Yeah? So we have learned that the data sits on those pages. Each of those pages gets a key. We learned that in the context already of the database buffer. So we have our logical pages. They have a specific ID, let's say 32 or 77. That's called the page ID. And I told you last time already, there's pages and blocks in the database system. But if I mean page 32 or block 32, it's the same thing. Page is typically used as that's data residing in main memory, block data residing on hard disk, on some persistent medium. But it means the same data logically. And page sizes may differ. You may configure them, some power of 2, 4K, 8K, and so forth, depends on your system. Yeah. So what we looked at so far is basically we started with the devices, whatever the device may be, and I told you, okay, there are physical pages like in the hard disk or on the SSD, and then there are virtual pages. That's the translation done by the page table. The virtual page ID gets translated to a physical page, but there's way more translating steps happening on top of that. The question is, how do I get from a relation being a set of tuples, and that's why I wrote it as a bubble here. So that's our relation. There's no order defined whatsoever. There are no duplicates. And here I only have 3 tuples in that relation. How do I map it to my virtual pages? So how would I do that mapping step? And the interesting thing is that sounds like something that's very technical, engineering, like a who cares decision, but it may have a huge impact on your database system. We're talking not about percentage, but orders of magnitude. Factor 100, 1,000. We had one case with a customer, factor 10,000. That would have been the change for that. Yeah? By doing that in one way or the other. There's a whole class of database systems where the major contribution was simply to change this mapping. And they got millions for their products and made a huge difference. And it's actually a very easy change, yeah, but it made a huge difference. Yeah. And so what we have to do is to create such a mapping is we have to linearize the tuples. Yeah? If you think about memory, if you think about the page, yeah, you have these linear addresses of bytes on your pages. So we have to somehow decide how to, you could also call it serialize, linearize the data from the tuples into the memory. Yeah? Maybe if you've seen serialization functions, linearization functions, every time you write something to a file on your operating system, that's a decision that has to be taken, and that's the same here. So one thing could be to write it in that order. You could say, okay, I first write the attribute values of the first tuple, yeah? 23, Albert, 45,000, something like that. Then I write the attribute values from the second tuple, that's this, and then from the third. Yeah, so one tuple after another. Yeah, that would be one way to write out those values. Another way could be to do something like that. I could say I first write out these tuple, this tuple, 23, Albert, 45,000. Then comes this tuple, yeah, and then comes that tuple. And that actually makes a difference when you do a query like select star from employees, because typically that is the order what you see in such a query. Yeah? So he would first get the tuple 23, then 77, 42, whereas on the slide before, it's a slightly different order, 23, 42, 77. Okay, so here you see see, sometimes in those queries you see that the order, how the data is stored, is also exposed to the front end. What is the difference? What is the difference in the results from this to that? It obviously differs, but how and why? I mean, it's the same query I'm using in both, right? So the idea should be I send the same query, it gets the same result at all times if I don't change the data. But here, obviously, I get a different result. Does that matter? Yes or no? Someone in the back rows. I mean, you can also play the game like you throw it at someone, like on weddings who catches the flowers, right? So that would be more fun. I think it would wake you up a little bit more. So what's the difference in those queries, in those query results? Yeah. So here's this one, 23, 42, 77. It's obviously a different order. Huh? 23, 77, 42. Yeah, there's someone. Maybe you throw again the box. We could also play like that. No, whatever.
The IDs are ordered ascendingly, so this could help us.
Yeah, okay. IDs are ordered ascendingly, and not on this one, but here, right?
Yeah, the first one,
yeah. Any other ideas? Yeah, maybe throw it back.
I mean, to make it like this, in order, it will allow us to use the index over the ID. It is really crucial for the database system to, like, for example, if we go to, because like to search for one tuple, it's always to first to look for the ID, and then it's kind of really the most hard.
Yeah, it's completely right. Yeah, we haven't talked about indexes yet. It points in the right direction. We will get there. For the moment, ignore indexes. There's no index, no data structure allowing me to retrieve data more efficiently. Yeah, I just have to read all of the data belonging to that relation. That's what I'm assuming here. Yeah? And depending on how I map the data to the device, like this or like that, the order in the query will differ. The question is, what is the semantics of that? Or is it a problem because the select star from it's always the same query, returning different results in the sense that the order changed, right? So why would that matter? Does it matter? Maybe someone else? Come on, don't be so shy. And that's someone else who. Yeah. Okay, cool. Yeah.
Maybe alphabetic order of the names.
Random. There's a more interesting question here. I mean, if you think about, I told you this is a set. Does a set have an order of the items? Everyone, no. No order, okay? Here's an order. Here's an order. Okay? So I made a mapping decision here to do it like that. So I define an order, which means when reading this stuff later on in this order, I have that order. So what does that order mean?
We control order.
We control order? Yeah, in mapping, that's true. But what does it have to do with SQL? Yeah, the box, please. What's this really light? This you don't see anyway. If you look into the
okay. Maybe because SQL will read it linearly from the database. So however, the insertion order was it will read it like that. That's why both SQL are the same, but the results are different.
Yes, exactly. Yeah, so for SQL, however that SQL gets translated into a program, different story, will, where am I? Here am I, genau. Will return it in the order very often as found on disk, unless I do what?
Order by.
Order by. Yeah, if there's no order by, very important rule in SQL, the order of the tuples has no semantics whatsoever. It's completely random. Yeah, you may never rely on the order of a statement if there's no order by here. Yeah, it may be that you always get the same order when doing something like that without the order by, that is not guaranteed, because that is typically only due to a physical organization, a mapping like that, an index, whatever. Yeah? So never exploit the order of the results of a sequence statement if there's no order by. Only if there's order by, it's guaranteed. And then the semantics, it's clear. Here it's purely random. Yeah, okay. So the answer here is also that it's the same result. This is the same result as that result, as the SQL has to live with multi-sets. Yeah. So you also see that in the tables where there are no keys defined, you can insert duplicates. That wouldn't be possible in a relation. Yeah. So it's a multi-set semantic, and typically no duplicates. Duplicates are allowed in SQL, not in relations. Yeah? So that's something that may be confusing. Here's another idea. What if you do it like this? So that looks wild, right? I first write out 23, then 37,000, ROP, 77, and so forth. Yeah? Along that, so basically what I'm doing here always is I define a path through my tuples, and that is how I write out the stuff. That would be one other option. Okay? Yeah, so basically those are two mapping steps, and now we look at them in more detail. So here what I do is the first thing is the first mapping step, 1a, how I call it here. So I map the set to a linearization order of the attributes of the tuple. So each tuple here has 3 attributes, and now I define an order that I use to traverse those tuples. And then again, of course, this data has to be mapped to bytes. Yeah, that's really where you look at, okay, that is whatever UTF string, and I use this representation on the byte level to map it. This is, on here the 77 might be whatever 4-byte integer or 2-byte integer, and then I use a certain byte representation to write it out to my virtual pages. That's 2 different mapping steps. Yeah, and we will look at them. We will look now in the following in particular at that 1a mapping step. So here again is the textual overview of those different mapping steps. So you first linearize from 2D relations. Yeah, that's what's happening here, to a 1D sequence of values, attribute values. 1b is serialization from a 1D sequence of values to bytes on virtual pages. Then the second is devirtualization. That's what we learned about with page tables and shadow storage and this stuff. Virtual pages to physical pages. And then physical pages to storage devices is materializing data on a storage device. It's actually, you would call it storing. We also sometimes call it materializing the data, because it's physically written and physically stored somewhere on that device. Okay, so this is one linearization I showed in that mapping step. And this is called a row-wise, no, I have too many slides here. So this is called a row-wise layout. So the idea is that you serialize the tuples one by one. It doesn't matter here whether you first linearize, sorry, I have to be careful, whether you first linearize this tuple and then that tuple. I'm just saying linearization happens tuple-wise, one tuple after the other. This layout is called a row layout, row-wise organization or row-wise linearization of the data. And this zigzag curve is meant to visualize exactly that. Yeah, that is the order how you go through that data to linearize it. The opposite extreme is so-called column layout. Here you first linearize all attribute values belonging to the same attribute. Yeah? So here we have 1, 2, 3 attributes. So I say I first linearize all those attributes. Then come those attributes, then come those attributes. Again, it doesn't matter. As with the rows, I could first linearize that attribute, then that attribute, then that attribute. The important thing being it's not tuple-wise. Yeah? You could also see it like that. It's not first in this direction. It is first in this direction. Yeah? And then when I'm done with one of the attributes, I go to the next attribute. Okay? You could also see it like that. I can only do it with the iPad, but not with the screen. If you rotate it by 90 degrees, it's the same technique. Yeah? Think again, a relation is a two-dimensional beast. Yeah, so you have two options of doing that. First in this direction or first in that direction. It's the same technique, row and column layout, if you rotate it by 90 degrees, clockwise or counterclockwise. Yeah, that's called a column layout. And why would that make a difference? Yeah, there's someone, maybe the box. Where's the box? Thanks. Ooh! Anyone injured? Okay. Okay. I think you killed it.
That's okay. So I think when we have like, I think the row layout might be better because if we add another tuple, we don't have to reassign the layout again.
Mm-hmm.
That's what I would guess.
So he says if we insert something, the row layout is better because we don't have to put it into different positions, but there's one position in the linearization order. Yes, very good. Yeah, so basically adding a new tuple could mean, for instance, appending it here. Yeah. Yeah, whereas if you do it in the column layout, that's your point. If I append it here, yeah, and then I have to fix all of those things here in many different positions. Yeah, as many positions as have attributes. That may be awkward. Yeah, maybe you? Try the box again. Maybe it's, I don't know, maybe no. Maybe there's a button or something.
Doesn't seem like it. But if we add a new attribute, we get the same problem for the row layout.
Exactly. If we add a new attribute, we have the same problem for the row layout. Assume I change the schema to have another attribute here. Yeah, then you have exactly the same thing happening here. You would have to change it here. Again, when thinking about the formats, it's 90 degrees, rotated, same problems. As with the storage layers, all storage layers have the same issues. Those layouts have the same issues, just rotated by 90 degrees. Also the same solutions, just rotated by 90 degrees. Yeah? So adding a column here, meaning changing the schema, is way more awkward. Whereas in the column layout, it's a piece of cake. You add it here, basically, zack, new column. Yeah?
We probably have more number of entries, so it's better to use row layout other than column.
If I have more tuples, you mean, or what?
Yes.
So you're saying if I have more tuples, I should use a column layout?
Yes.
Not necessarily.
No, not column layout. If you have more tuples, it's better to use row layout because it's more.
More tuples than attributes, you mean, or?
Yeah, compared to attributes.
Yeah, depend. No, it depends on other things as well. We tap into that soon. You raised your hand.
If we create the queries with the data, not just adding tuples or attributes, then maybe the column one is better because then we can get the whole attribute. But yeah, at the same time, we also have that problem what you said about rotation because we might want the tuples and not the attributes.
Yeah, we can't have it all, right? So we have to make a decision. Actually, you can have it all. We will get to that. But yeah. Yeah, think about queries. I mean, talking about queries. What does it mean for queries? So we said, okay, the insert. Someone said insert is easier on row layout, column not so much. Yeah. What about, yeah?
Especially like there is a database that the tuple is super long, and you want to like do some statistical analysis about that, and to use the column layout, you just need to take this one long
Yes.
column, and
Yes.
it will be much faster.
Yes. Perfect answer. So in particular in a case where there are many attributes here, yeah, that's what it was said. In typical analytical scenarios, you have many tuples. Yeah? For the 3 tuples, you don't have to worry about that. That's just for the purpose of the slide. But if there are millions and millions of tuples, and you assume you have many more columns, yeah, what it means is if you do analytics, any statistics, and you don't select all, you don't have a select star, but you have a select of certain attributes in your query, You only pick those attributes, and they're relatively easy to read from the storage medium. Assume if I only wanted to have those guys here, yeah, I just go to this position, and then it's a sequential access operation. That's way faster. In particular, again, if you think about the random versus sequential I/O problem we talked about, yeah? This is so much better and so much easier to do because you have a couple of sequential operations. Yeah? So bottom line, in particular, in how do I say messed up and political correct? Messed up schemas. Yeah? If there are many, many attributes, typically a hint that the schema is, has a problem, but you will see that in real systems, many, many attributes, hundreds or thousands of attributes in the table, then that makes a difference, a huge difference. Correct. Yeah? Whereas the row layout is more beneficial if you query many or almost all of the attributes available in that relation. Then the column layout actually is not a good idea. It's a better idea to use a row layout. Now the question is, how could you know in advance whether your queries want to have all or many of the attributes versus just some of them? Because you have to make the decision ahead of time and not at query time when the query comes in. So you have pros and cons of both of those approaches. Yeah, here are some example queries for row layout that work well. You note that here is always a select star, all attributes. The insert we discussed, yeah? Insert is beneficial here. Also delete from, you delete one or multiple attributes, that's all fine with row layout. So row layout is easy to implement, good for transactional workloads meaning many change operations. Good if you access only single rows. But it's not ideal for analytics, that's a problem, and not ideal for wide tables as we had in the example with many columns. So here are example queries that work well in a column layout. So typically you have something like few attributes being selected, and then there's typically some sort of search condition. But the important thing is you only are interested in data from few columns. So what are the columns in this query that you have to read? First query here, which columns? I almost said it, or did I didn't. Which attributes have to be read here? Someone else? Yeah?
City code and name.
Yeah, city code and name. It's not only city code, yeah, be careful. That's the stuff that's being displayed. But name I have to read in order to be able to evaluate the condition. If there's no index, if there's an index, does it work for me? I don't have to do that. But if it's a scan, so basically I have to scan all of the tuples, I really have to read them. It's those two attributes that I have to look at. So two portions from that linearization order. Okay, again, so those are the advantages. So it's good for single to few column access, good for analytical workloads. Not ideal when accessing many attributes, not ideal for transactional workloads. So for column layouts, there are actually a couple of options. Yeah? And that is what we're now trying to do is we try to get the best of both worlds, row layout and column layout. So again, we have the three tuples, and that is a column layout I just explained. And how you implement that in the database is often through some implicit key mechanism. So assume arrays. Assume you have three arrays. Array 1, this is array 1, array 2, and array 3. So basically then there's an implicit key here. That is array slot 0, 1, 2. So by that you could address each and every cell in those arrays. Yeah, that's called an implicit key. But you could also make it explicit. Where's the explicit key? Here's the explicit key. Yeah. So again here you could actually scramble, have different orders along the different column representations. So basically it's here you have the key signaling, okay, that is the row it belongs to, and that is the value in attribute ID, and so forth. So basically here that would be one tuple, that would be another tuple, and that would be another tuple. That's also something database systems did. Probably you won't do that anymore today. Should I don't know, let's skip over that. Oh, no, maybe let's briefly explain that. Yeah? So, I mean, one thing you will see if you have a column-wise representation is at certain times when you want to retrieve more than one attribute value, you have to correlate the different entries. So if I have an implicit key representation, I know that these guys belong together. Yeah, that's okay. But if I have an explicit representation, as I showed you before, I know that those guys here belong together. Yeah, and basically that means if I have any query where the select, or I'm selecting more than one attribute, as in the query we saw before, as name and city code, I have to somehow reconstruct the tuples. Yeah, I have to I have to glue the attribute values from the different attributes together again somehow in order to be able to I mean, they belong together conceptually anyway, but how do I bring them together? And if I have a representation like that with an explicit key, like here, where the order may differ across the different columns, that may be slightly more work, of course, because I actually would have to join those relations together. Yeah, that's just one thing to keep in mind here. Okay, I think we can skip over that. But finally, what I would like to do in the remaining time today is talk a little bit about other layouts that try to achieve the best of both worlds. There's no free lunch. You always have to pay a price for those layouts, but you also gain something or get a good compromise. And here are 3 examples. So assume we have a workload containing both of those queries. And that's basically what we just alluded to. We have a query selecting all of the attributes, maybe accessing one specific or few tuples. So a row layout is beneficial. And at the same time, or sometimes, doesn't have to be at the same time, but basically sometimes you have queries like this, sometimes you have queries of that, like that on the same relation. So this query obviously here on top is more like on the row domain. Row layout would be good, and this would be more on the column domain because it's just a single attribute. So what do you do? Maybe you tell me without looking at the slides ahead of time. What could you do? I mean, you have to make a decision, right? Do you use row layout or column layout? Assume every odd query is this, every even query is something like that. What do you do? Yeah?
We can, like, one database use the column layout, one for the
row
layout, and we do the first one, then we go to this one.
Yeah, exactly. Very good. So that's one thing you could do. That's called fractured mirrors, for whatever the inventors wanted to do it like that. And what it means is you represent the relation in both layouts at the same time, in row layout and column layout. And try to depict it here. Here it's maybe a bit easier. So I say I don't do a single linearization round over my tuples. I do 2 or 3 or 4 or whatever. We had a project where we did 3 actually. And then we routed the queries. We inspected each and every query and said, okay, if that query is more on the row layout, we send it to the row representation. If it's more on the column domain, or that's more beneficial, we send it to the column representation. Yeah. So that is how that would look like. Swiping doesn't work again. Yeah. So you have 2 copies of the table, and you can route your queries depending on whether a column layout is more beneficial, like here, or whether a row layout is more beneficial. So what are the pros and cons of that approach? Yeah, someone else? Advantages and disadvantages of something like that. You keep the relation, you keep the data in 2 copies physically. You materialize it twice on your storage device. Yeah?
This is costly. I mean, first of all, we use double the storage space, and also every time we write, we have to write on both versions of the database.
Yeah, we waste storage space. We have to pay it twice. You say it's costly. Depends on how much data, because storage is so cheap these days.
I mean, costly like cost of operation. We have to write on something, then we have to write on both.
Yeah, that is more critical. So if you do a change to your relation, you have to write in 2 places. And that's one of the fundamental rules in computer science. Don't do that. Don't keep data twice, multiple times. because then that leads exactly to these kind of situations. So assume that you do a change, but you only change it in this copy, not the other. Then you're inconsistent. Yeah? Depending on where your query goes, you get different results. That's bad. Yeah? That's true. Yeah?
And no matter what we insert, we always have one disadvantage. Like if you insert
Yeah.
a new tuple, you get a disadvantage from
Yeah.
the right one, and if you insert a new attribute, you get a disadvantage of inserting the left.
Fantastic. So I lied to you. It's not only the best of both worlds, it's at the same time the worst of both worlds. Huh? Yeah? Whatever you do, here you have an advantage and a disadvantage, and you have a disadvantage and an advantage. Yeah? And then you can add up the costs. Maybe overall it's better or worse. I don't know. Yeah? But there's a price you pay. Yeah? Very good. Okay. So what do you do? What would I do here? So again, you have these kind of queries on our very simple relation. Okay, real relations have way more attributes. Here we have one query selecting those two attributes, another query selecting that attribute. Yeah?
Can we have a system where we have a threshold of number of attributes, and based on that threshold we decide if we use row or column layout?
Yeah, okay, that alludes, okay, that's what's being done. So actually that's what we're doing it manually now. Yeah? So we have the queries, we analyze the queries, and we make a decision on a particular layout. And that's basically an optimization problem. You could say, okay, depending also on the frequency of specific queries and on the execution times, you can make a decision on how to linearize your data on the storage medium. Yeah? That's absolutely right. But now if you do it manually, like here in class, so what kind of layout would you use? Would you use row layout, column layout, or are there other options? And maybe someone else? Okay.
We would use row layout for ID and name, and then at the end we have column layout for city code.
Right, that's the right solution. Something like that. Yeah, basically you would say this is row layout on those two attributes, that's what you said, and then it's a column layout on that final attribute. That's called vertical partitioning. Yeah, if you recall, horizontal partitioning in a relation means you chop the relation into pieces along that axis. Now I chop it into pieces along the vertical axis, along the different attributes, and I say, okay, I make a cut here, and within those attributes I do a row layout, and within that attribute, is it column or row layout?
Why we don't use a column layout for the first one?
Okay. For the first, because the query says, whenever I touch those attributes, I touch both at the same time. So if you use the column layout, it could be that they are adjacent, but still then you have problems like I first read the attribute values from ID, buffer them somewhere, and then I need them from the second and stuff like that. Or it could be the case that in the layout, in the linearization order, the two attributes are not adjacent to each other. Yeah, there's ID, there's a lot of stuff in the middle, then comes name. So it's different places. May lead to more random I/O, depending on your storage. But it's not the perfect scenario. They're already put together on the storage medium. Yeah?
But it's called vertical partitioning because this approach is mostly by row. Like it's more likely to use a lot of rowing layout, and then you are in the vertical, the column partitioning.
Maybe. No, it's called vertical partitioning because, I mean, if you really think about, do we have a relation somewhere on the slides where I can scribble that in? Here, this is an extreme form of vertical partitioning. Each column becomes its own vertical partition. Yeah, and what we did now, in that example, is I said, no, those two attributes, ID and name it was, I think, I don't remember, that is our vertical partition. Yeah, and that is another vertical partition. It's really like horizontal partitioning is saying, I partition the relation along this dimension. Yeah, this tuple goes in one partition, and those two tuples, for instance, go in one horizontal partition. Again, 90 degrees rotated, vertical partitioning along the attribute names. Yeah, and then we are back in this example. Where are we? I missed this one. Yeah. So where we say, okay, basically it's a vertical partitioning. I say, okay, I have one vertical partition representing those attributes and another representing that. And here I used row layout. This is row layout. Okay? What is the layout here? Is it row or is it column? Well, on the far right, yeah? Yeah, it's actually both. That is correct. Because if you have rows that only have one attribute, there's no difference to a column layout. No difference whatsoever. It's row and both column layout at the same time. Yeah? Yeah, and then you can play a lot of games. Here's another example. What do you do here? So first, query selecting. We have 10 more minutes because one layout I have to tell you for the project. ID and name, and here it's city code and name. So name appears in both. In the previous example, it was disjoint, yeah, with disjoint sets of attributes. Now it's not the case anymore. Both query name and one other attribute. So how would I do that one? Yeah, someone else? Yeah?
We have two partitions with naming both.
Yes, that's one way of doing that, but what does it imply?
Name on both sides, so name is right.
Your name is replicated, yeah, as before. In the fractured mirrors, it's partially fractured mirrors, you could call it. Partial redundancy, meaning here we have the names and here we have the names. Yeah, that the IDs are only here. And the salaries here, or what is it, city code or something like that, is here. Yeah, so it's partial replication. Yeah? That's another game you can play there. Yeah, this is just, so you can compute how many number of vertical partitions are possible. That's an optimization problem. There were research works that did exactly that, given a number of queries, try to optimize the vertical partitioning, and so forth and so forth. The good thing for you is to remember, forget about it. It doesn't make sense. It makes sense conceptually, performance-wise, forget it. The only thing you need to know about is row and column layouts. They make a huge difference. In theory, you could get slightly better with vertical partitioning than column layout, but it's not worth the effort of implementing that, honestly. Forget about it. We had some research works in that space as well. What makes a difference are hybrid or so-called recursive layouts, and they reappear over and over again. I think there's one name missing, actually meaning the same thing. It's all the same, whether you call it Pax, Parquet, or a newer name for that is Arrow. It's the same idea, and that works as follows. That's called a recursive layout in the sense that it's a little bit like a recursive curve in the sense you say, okay, I first partition my data horizontally. So here we have the horizontal partitions again. Yeah, 4 horizontal partitions. And within each horizontal partition, you do a column layout. Okay? That such a block here is called a Pax block or Parquet block. Yeah, there's a variance to that in the context of our research group. They're called a Pax block. Yeah, so that's one block. And the interesting thing is, with that, you have a good trade-off of the properties of those of that data. So here's another example for such a layout. The only thing I'm changing here from here to there is the number of tuples. Here it's 6 tuples in a block. Yeah, previously here it was 3 tuples in a block. But whatever I do, I say inside a block I do a column layout, whereas across blocks it's a row layout. And what might be a good thing about that? What might be a bad thing about that? Yeah, and the red pullover.
We don't have a waste of the storage here because we don't copy the data.
Yeah, there's no replication like in the fractured mirrors or partial redundancy. That's very good. Yeah.
And insertion or deletion of specific attribute or new data.
Yeah, insertion, but you could do something like that you insert it here after the first 6 tuples, right? Then you only have to cut through one of those lines. Yeah, of course, if it's in the middle of a block, it's the same problem as in column layout. That's true. Yeah, that's right. What other, yeah?
When we need one or two attributes, we still can read sequential blocks, like relatively when they're not big, when they're sequential.
You mean if you read all tuples, or I didn't get that?
When you read one attribute of all tuples.
Okay, yeah, that's true. That may happen. There you have to be careful with the minimal units of the storage medium that you can read. But in particular, what it means is those Pax blocks in practice are relatively big. So it's not just like 6 tuples, it may be thousands of tuples. And that means within such a block, you can still read sequentially across a single attribute value. So it feels like column layout. Eventually, you're at the end of that Pax block and you have to get to the next block. But it's more or less, it's close to a column layout or the performance of a column layout. So the more analytical you get in such a layout, the bigger those blocks will become. Because then they are the most efficient. So here's again a visualization of that. So basically that's a block or horizontal partition, and then within such a partition, you do a serialization. Does anyone see another thing that becomes possible with a layout like that? In particular, if you think back about pages in the database buffer or blocks in the hard disk. What other interesting thing happens here or could be possible with a layout like that? Yeah, green Pullover? Yeah. Yeah, that's a different story that goes in the direction of indexing. We do all of these things, a separate story, and it's kind of orthogonal to this thing. Yeah, I always have examples today in the lecture. Oh, we want to have the tuple, we have to scan all of the stuff. No, we don't do that, of course. Yeah, there are many things that can do that more efficiently. Separate story. That's not what I mean. I mean something different, some other idea. If you organize your data like that and assume each block magically corresponds to a page in your database buffer, what does it actually mean? Yeah? Assume that this is a page here in your database buffer of 4K, and that is a page. And here you have tuples, and here you have tuples. And what is the advantage in particular when you think about how would that work in row layout versus column layout? Yeah, the only thing
You will have too many partitions if you are trying to get a specific column attribute, because you will have a lot of fragmentation for like the last column, for example.
Yeah, that's right. You lose the advantage of being able to do a column scan, column layout style scan. That's correct. If the pages get smaller, that's what I said before, the more analytical you become, the more it's in the direction of selecting few attributes and doing large scans. You want to have large blocks. If it's smaller blocks, it's not such a great idea. Yeah? But assume you're more on the transactional side, and sometimes you're a little bit analytical. And then you do something like that, where the block size corresponds magically to your page size. Each block or each page is basically a black box, you could argue. And in this layout, all data within a block stays on the block at all times. So what I'm doing here is I'm just changing the layout inside the block. Inside the block, I'm saying now it's column layout. Maybe previously it was row layout. No matter what I do within the tuples stay within the same block. This means in query processing, I could actually change the layout. Actually, how this was invented was there was a database system that was in row layout, and people thought about, oh, how could we integrate some column-style layout into the system? And they found, oh, that would be a major change because everything is organized around pages. So what did they do? They changed the internal representation of the pages into a column layout, which meant the rows, the tuples would still sit on the same pages. No change to the outside system. They would always find the tuple on the page. However, within the page, there was a mechanism redirecting requests to the column-style layout inside a block. Okay, so that's it for today. So on Friday in the lab, my PhD student Emmanuel will explain a little bit about Mutable and the first milestone in the project, because that deals with data layouts, row, column, and pegs, and you should implement that. See you next week, latest. Thanks.